today is about regret minimization. And we're going to do it using this algorithm that we will use it throughout until the last class of this course. It's called Multiplicative with updates, which is a really powerful one and has been discovered many times. And we're going to see it today. But just to start again, just to begin, the point of this class is still on the same theme like last class, which is how do you optimize for the future, which you don't know, how to handle uncertainty, right? And last week we have seen online algorithm, and what we use is competitive analysis. Okay, we've seen ski rental and online set covers. So those are examples. And yeah, so this is one framework to get some formal guarantee that you are making good decision even with some uncertainty. Today we're just gonna look at another framework. It's called regret minimization. Okay, and what's the theme of this regret minimization? So it's like this. It's like when you have some fixed set of strategies for something, and on each day you don't really you need to choose some strategy, but you don't know which one is good. Okay, and what you want to know is you want to identify a good strategy. You want to perform as good as you know in hindsight which one is a good strategy. Okay, so this is all vague and high level. We're gonna see now. Okay, but this is a topic. This is the name of the topic. Okay. All right. Okay, so let's be more concrete. So let's say that you think you wanna decide whether you wanna buy a stock or not, right? So on each day you decide whether you wanna buy or sell a stock, and in a stock market, and let's say that there are experts. Okay. So and this expert will tell you whether to buy or to sell, to say that whether the price will go up or down. Yeah. So on each day, the following will happen in order. First, each expert eye will predict whether the stock price will go up or down, right? So each of the experts say whether it's up or down. There are n of them. And then you need to basically choose which decision, which action to follow. Whether you say that it's up or down, you choose that. And only when you, as an algorithm, commit to your decision, then the nature or the adversary will review what's the actual outcome. Okay. And the actual outcome can even depend on the algorithm. So that's why we call it adversary. Okay. It can be that you say up and then the adversary just say down. Okay. Right. So we don't assume anything about adversary. Okay. And so what we want to do is to minimize the total loss, which is to minimize the total number of mistakes that we ever make throughout every day, summing over all days. Can we don't make too many mistakes? Okay. So at first this seems hopeless, because right now I assume something super strong about adversary. Right? I don't adversary can even review outcome depending on our decision. So we can make mistakes all the time. Okay. But what we're going to do is first, I will just assume that the adversary is not too strong yet, and then let's see how we get some meaningful guarantee. And then after that, we will see that we can, even if we assume that adversary is super strong, we can still say something meaningful. In what sense, you'll see how. Right? Okay. But is the setting clear? Any question about the setting? All right. So let's see this. Suppose that I assume this. Suppose that I assume that there exists a perfect expert. That is, there is one guy among the n experts that is just never wrong. Okay. So this, if I assume this, I implicitly assume something about adversary as well, right? Adversary cannot, like, at least need to be correct, like need to follow the perfect expert. Okay. But anyway, suppose that there is a perfect expert. Okay? And what if I just do the following algorithm? On each day, I look at all the experts. Okay. And then I follow the majority. So I look at all the experts with no mistakes so far. Okay. And then I follow the majority. Like if most of the experts say yes, say up, then I say up. If most of them say down, I say down. And then once I decide to say up or down, once the adversary review the actual outcome, then the expert that make a mistake, we kill all of them. And then we look at the remaining expert and follow the remaining majority. Okay. How many mistakes can we make with this algorithm? Yeah.
At most log n, because if you make a mistake, it means that half of the experts were wrong. So you get to basically cut off that half, and you're never looking at them again. And just that'll happen log n times until you find the perfect S-verb.
Very good. Yeah. So with this algorithm, right, the number of mistakes that we're going to make is going to be at most log n. Just because whenever we make a mistake, we know that more than half, at least half of the experts are wrong. So we remove half of the experts. There are n many experts for each mistake. Like for each mistake, we remove half of the experts. There are n experts, so there are like log n mistakes that can happen. Okay. Good. So with this, if there exists a perfect expert, then the total loss, like I use L for the loss and A for the algorithm, the total loss of the algorithm is going to be at most log n. Yeah. So that's good. So this is when you assume that there is a perfect expert. But what if there is no perfect expert? Okay. Now it could be the case that like we always make a mistake. But like how, like in what sense can we say something meaningful? And here is the idea. The idea is that maybe let's try to compare our loss with the loss of the best expert. Okay. So that's the idea. So if we look at our loss, but we are not too bad compared to even the best expert, we are not too bad. Okay. So and I let L star to denote the total loss of the best expert. So this is like the number of mistakes made by the made by the best expert. Okay. So let's try to see what would be the algorithm that would work, that would have some nice guarantee. It's just iterated halving algorithm. Okay. So what we're gonna do is this. We're just gonna divide the time into epochs. And on each epoch, we run the halving algorithm. Okay. So what do I mean by this? Like suppose that in the beginning, I just run halving algorithm. That is, I just keep track of all the expert that's not queued yet. Like that make no mistake so far. Okay. And once I make a mistake, I queue the expert. Just do that. But once there's no expert left. Once you don't have anyone left, then you just say that you start a new epoch. Yeah, question?
When you start a new epoch, so let's say in like the second epoch, are you only going to be taking all of the experts with one mistake, or will you take all of the experts even if some of them made like 5 mistakes in the first epoch?
We're gonna just revive everyone. Yeah. Okay. So it makes sense to say that okay, the one who makes so many mistakes, we shouldn't revive him or her, but let's say that I just revive everyone. Okay. And even this simple algorithm, we're gonna get some nice guarantee. Okay. Is the algorithm clear? Good. So our goal is this. We wanna that now upper bound our loss by the loss of the best expert. Okay. So what I'm gonna do is maybe I just gonna say that let's look at the number of epochs. Do you see how can we bound the number of the total loss, our total loss, by can we upper bound the number of our total loss in terms of the number of epochs? Anyone?
Would it be
in each epoch? How many loss can we have? How many log n? Right. So this is going to be at most log n times number of epochs. Log n number of epochs. What about like the best expert? Can you lower bound? Can you get a lower bound for the number, number of loss, like the total loss of number of expert in terms of epochs? Anyone? Anyone else?
This is assuming like the same set of experts, but just also with the best expert?
Yeah.
Okay.
So on each epoch, what do we know? We know that every expert must have made one mistake because they are all queued before we start a new epoch, right? So now, so it means what? It means that if there are, let's say, like 10 epochs so far, even the best expert must have made 10 mistakes. So this thing is just going to be at least number of epochs. Actually, -1. If there are 1 epoch so far, like there might be still. So actually, yeah. So actually, this is like number of epoch -1. Okay. So with this, we just can combine them, and then we get that this is just going to be at most log n times L star plus 1, which is basically like L star log n plus log n. Okay, so we get some bound. Like we said that we have that our loss is not going to be too bad compared to the best expert times log n. Okay. So this is like there's some kind of guarantee that we can show, even if like the adversary is so bad, we can still compare ourselves to the best expert. Okay. So this is what we got. Okay. Right. Now, in your homework, you will show this. You will need to show another algorithm that you are as good as the best expert up to a factor of 2, and some additive error here. How to get this? You should get like some inspiration how to get this by the end of this class. So with like basically with some small additive error like log n, you can match the best expert up to a factor of 2. And the idea is just that maybe we shouldn't, like if one guy make a mistake, we shouldn't kill him immediately. We should do like maybe like be more lenient. Yeah. Okay. But okay. Now you may ask, can we get better than 2? Like suppose I want to be like as good as the best expert up to 1.99. Is this possible? So I want to say that actually no, you cannot. Let's say that you have just 2 experts, right? 2 experts. One is like this guy say always up, this guy always says down. Okay. And if the adversary, like, let's say that whatever you do, like you just choose up or down, right? And how would you prove lower bound as an adversary? Maybe just say that adversary just say like make sure that you make a mistake every day, right? If you say up, it reveals that the actual outcome is down, and vice versa. Okay. So I said there is an adversary that guarantee that our total loss is going to be at least 2 times at least 2 times L star, the loss of the best expert. And okay, how? So if the adversary just review the opposite outcome on what we choose, we know that after t days, our loss is t. Just we make the mistake every day, but the best expert will have loss at most t over 2, right? Just because like one of the expert, like if we choose up less often than down, then the up expert will make less than like a half of the number of days, less than t/2. So yeah, this is like a simple argument why we need to be like we need to pay a factor of 2. Good. Questions about this? Okay. Yeah.
Can you also formulate this problem with like more than 2 options?
We're gonna do
Say
it
there
now.
were 3. Oh, okay.
Yeah, we're gonna do it soon. Yeah. Right. Good question. Yeah. So you anticipate me. Yeah. So, right. But let's conclude a bit. Okay. I will conclude with some notation so that I can like use this notation in the next part. Okay. So in the setting when there are n experts, and on each day, expert I will experience a loss, whether like the loss here is just like the loss is 1 if he make a mistake. Okay. And know that L, like the loss of expert I at day t, is chosen by the adversary, right? After the algorithm choose an action, and the algorithm loss is like whether like the algorithm loss L of the algorithm at day t is 0 or 1. So it's 1 if we make a mistake. Okay. And Li is the total loss of the expert I. L star is the loss of the best expert. And La is the loss, the total loss of our algorithm on every day. What we have seen so far is that when there are 2 distinct actions, like up or down, you will show in your homework that there is an algorithm that achieves like within a factor of 2 with the best expert. And we also say that we cannot do better than a factor of 2. Okay, so note this notation, right? L star, La, and Li. And like the big L is like total loss, and the small L is like the loss on each day. Yeah. So basically, this factor of 2 is tight when you need to choose 1 out of 2 actions. Okay. Now let's look at the more general setting. So what I want to do is now like it's more general in the sense like we are not restricting ourselves to like 2 actions. Okay. So let's say that now instead each expert has its own suggestion. You can say that maybe there are n many stocks, and each expert, like on each day, they will just suggest 1 stock, and you choose which stock to buy. Okay. So each expert just has its own independent suggestion. Okay. There are n distinct actions to choose on each day, not just up or down. And let's say also that each expert on each day can lose or can also gain. We don't just count the mistake. Like we might make a mistake gain profit. So basically on each day we don't just choose up or down, we choose which expert to follow. And also here is a really important one. We allow ourselves to be randomized. What do I mean by this? I mean like we choose distribution of expert. We're gonna choose expert 1 with probability P1 and expert 2 with probability P2 and so on. And then we compute the expected loss or gain that we get on each day. Yeah.
So in this problem, can the experts still pick the same suggestion if they wanted to?
Like you can think like that, but it's just easier to think like, yeah, each expert has, like, it's just that each expert has different suggestion, and basically I want to say like the loss or gain on each expert are just independent from each other. So like so just think of this maybe, yeah. They have different suggestions totally. Yeah. Okay. But if they choose to give the same suggestion at all time, then basically the loss or gain that they have gonna be the same at every day. Yeah. So but now I don't restrict that. I just say okay, the loss or gain of each expert is just independent from each other. Okay. So formally to capture all these things, formally what do we have? We have this. There's going to be n expert and t days like before. On each day, the following happen in this order. First, we choose the distribution of expert. Which one to follow, right? We follow expert I with probability PIT. So this is like some number between 0 and 1 that the sum of them is 1. It's just a distribution. Okay. And once we commit to our distribution, then the adversary review the loss vector L1, like LIT for all I. This is the loss vector at day t. So what does it mean? It means that the expert I loses money by this LIT. So if this is 1, it means that this expert make a mistake fully, like it lost 1 money. If it's less than 1, if it's less than 0, it means that the expert gained something. Okay, so like this is a loss, not gain. Like this is, if it's 1, then you like the expert lost. Okay. And now the important thing is that, again, like I allow the adversary to be really powerful. This loss vector can depend on P, on the distribution. And even the entire history, like it just, yeah, okay. And what do we want to look at? We want to minimize our total expected loss. So what is the expected loss? It's just this one, right? Because we're gonna choose expert I, and we're gonna lose by this much with this probability. So this is like our expected loss on day t, which is just the inner product between the two vectors. Okay, so quite a bunch of notation. Are we good so far? Yeah.
What is the goal of the adversary? Is the adversary trying to maximize our expected loss, or is it trying to make our outcome the most different from the best expert? Like, what's the goal of the adversary?
You can say that the goal as the adversary is like to make our loss to be really far from the best expert. Yeah. But yeah, we're gonna see soon that no matter what, even in this really general setting, our loss will be comparable to the loss of the best expert. There is an algorithm that can do that. Okay. So I want to emphasize one thing. We said that adversary is really powerful. That is, it like the loss vector that it review can depend on the distribution P on each day, but it cannot depend on which expert we sample according to this distribution. Okay, so it sees the distribution, but it doesn't see which guy we really sample. Okay. So like this is like the power of randomization that the like at least the adversary don't see which expert we sample, and we're gonna say that like this is why this randomization will help us to beat this factor of 2 that you have seen. Okay. So like before, our loss is just the total loss of our total loss LA is the total loss on every day. Expert I total loss is Li here. The best expert I's total loss is L star, which is the mean of L all I, mean of Li for all I. And here is what we define. It's called regret. Regret is just the difference between our loss and the best expert loss. Okay, this is basically the cost of not knowing the best expert in the beginning. If we have known the best expert, the regret would be 0. Okay, and we will say that some algorithm has no regret property. If the regret will grow like it's kind of will grow like in order of small of t number of days. The way you should interpret this is like as number of days once the number of days goes by, as time goes by, then you have no regret on average. The average regret is kind of converged to 0. So far, all the algorithms that we have seen have regret, right? Like you have seen the algorithm where like this is at most log n times L star. This is like has a big regret. We want the one such that this is kind of 1 plus little o 1 times this thing. This is when it has no regret. Okay. So that is actually the whole area of research, studying algorithm with no regret, and it's called regret minimization. Okay, so what algorithm should have no regret? Like, how can we do anything at all that is meaningful? So one idea is okay, we absolutely have no control over the future. Maybe we just rely ourselves on the past. Okay. The idea is to follow the leader. For example, like just choose an expert, the best expert so far from the past, like the guy that makes least mistakes so far, least number of mistakes so far. Do you think this is a good algorithm? Yeah.
It's going to be bad because the adversary can see our probability distribution. So if we do like a 1 and a bunch of zeros, they'll just like make that wrong.
Mm-hmm. So, like I claim that this algorithm, you even in the 2-action setting, you can still pay this much. Okay. And because it's really the same lower bound argument that we just discussed. But let's say that in general, the point is that actually as long as you choose just a single expert, then there will be regret. Okay. So so basically, we're gonna answer the above question negatively in a very strong way. So That is, suppose that on each day we choose only one expert. Okay, which means that on each day, PT will look like EI, where EI is like a vector with 1 on the ith row and 0 everywhere else. Okay. So we're gonna say that like as long as we choose just a single expert, which means like we choose one expert on each day deterministically, then you're gonna have regret. So, okay. So suppose that on each day, the loss vector actually is between 0 and 1, so that there is no gain. Okay? There's gonna exist adversaries such that our loss is just t, the number of days, but the loss of the best expert is t over n. So our loss is n factor worse than the best expert. Okay. Can you suggest how should we prove this? As long as you choose one expert on each day, how would you come up with an adversary such that the loss is like loss of our algorithm is t? There's like a really natural one, straightforward. Yeah.
Is it not what Scott said before, where the adversary just like chooses the in the loss factor, the loss to be all on that one expert that we choose?
Exactly. So if we choose expert I, then just set the loss vector to be like of that expert to be 1. The loss of that expert is 1. Everyone else have 0 loss. Okay. And just do that. And we just gonna get that our loss is t, because we just pay 1 per day. But why would the best expert will have at most t over n loss?
Because like let's say the first time we pick randomly just because there's like no best expert so far. So then that expert's going to be wrong, and so all the other experts will be like 1 and 0, and we'll pick one of those random ones, and then that expert will be wrong. And basically, so we'll be iterating over all n of them, and we'll get n loss, and each of them will only get 1 loss, and then we can just like repeat that process over and over again.
So like right now you assume one particular algorithm where you choose some, like you kind of iterate over all expert, but like this is going to be true for any algorithm, because basically you just said that okay, whatever algorithm is, right, whatever algorithm is, as long as it choose one expert on each day, then there's going to exist an expert that is selected least often. How many times that expert is selected? At most t over n, because there are n expert, and on each day we select 1. There are t days over n experts, so the least selected expert is selected t over n times, and the loss of that expert is going to be at most t over n. Okay. So yeah, just to repeat, we're going to choose, like if algorithm choose expert I, whatever this algorithm is, if it choose expert EI, like I, then the adversary just set the loss vector to be EI. The loss of the algorithm is just t. We pay 1 per day. But there must exist an expert with that we choose at most t over n times. So that that guy, if this is like I star, the loss of I star is just going to be at most T over N. So L star is more at most T over N. Okay. So you can use the same you can use the same argument to say that, okay, now if once we allow like a loss and gain, like the loss vector is between 1 and minus 1, then our loss can be as big as T, and the best expert loss is just like actually kind of almost negative T. Yeah.
Is it this is just like I don't fully understand this. Can the adversary choose like everyone loses like with amount 1, or is that like a distribution where it has to like
No.
sum to 1?
No, like the adversary can choose like the sum of the loss doesn't need to be sum
Okay.
don't need to sum to 1.
Okay.
Yeah. It can choose like the loss vector can be like 1 and then minus 1, minus 1, minus 1, something like this too. So there can be, when there are both loss and gain, yeah, like basically our loss can be T and the best expert loss is like basically minus T. So it's totally different world, like positive and negative. So the point is that as long as you see that as long as we choose expert deterministically on each day, like that is we put the probability mass to just one guy on each day. There's going to be a lot of regret. You cannot avoid that. Okay. So which in particular it means that you cannot just follow the leader. Just choose one single leader. That's going to be bad. Okay. And to get a good bound, we need to be randomized. We need to choose distribution of experts. Okay. So, but it turns out that, and here is the algorithm that works. It's called multiplicative weight updates. And this is actually going to be very close to follow the leader. It's really just some softer version of following the leader. So let's look at the algorithm. Yeah.
Is this similar to boosting?
It is. It is the same thing.
Okay.
Yeah.
That seems very similar.
So the algorithm has like parameter epsilon. Okay. And in the beginning, just set the weight of everyone to be 1, the weight of every expert I to be 1. And on each day, we're going to follow the expert with probability proportion to the weight of WI. Okay, so this is just to normalize to make it proper distribution, but you just follow the expert with probability proportion to its weight. So give this distribution. So in the beginning, you get uniform distribution. Just choose random guys. Okay, that's the first round. And once the loss vector is reviewed, you should then just update the weight in the way that makes total sense. That is, if the loss is 1, then it means what? The weight of expert I on the next day is just going to reduce by some small factor. Yeah.
Does epsilon need to be less than 1? Like, is there a bound on epsilon?
Epsilon good question. Epsilon is between 1 and 0. So if epsilon is 1, it means what? It means that we kill the expert. Like if epsilon is just 1, and suppose that the expert I make a mistake fully, then its weight is going to be 0. But yeah, we don't want to set epsilon to be 1 actually. Yeah. The best one is not to set epsilon will not be 1. Yeah. If like this is negative 1, then it means that like we're gonna increase the weight a bit. So that's the algorithm. We update the weight and then go to the next day, follow the expert proportion to the weight. Question about the algorithm?
This is a question about something earlier. Is it either -1 or 1 for the loss or gain, or is it somewhere in between?
It can be somewhere in between too, yeah. So if the loss is just 0, then we update nothing. Good question, yeah. Okay, and this algorithm have a really like a intuitive explanation, right? So you can think like the weight of expert I to be like its importance, and we in the sense that we follow each expert proportion to its importance. Initially, all experts have the same importance, and if the expert I loses a lot, then we decrease its importance a lot. If it's gain, then we increase the gain, increase its importance. And epsilon is just how aggressive we decrease the weight. If epsilon is 1, it means that like if some guy make a mistake fully, then we kill it. And you see that this is kind of softer version of follow the leader. In a sense like, okay, if all the weights are basically the same, just choose random expert. But if actually there is some expert I that perform much better than everyone else, we actually gonna like basically surely choose the expert I. Okay. All right. So now let's analyze it. Okay. And this is gonna be an algorithm that has no regret, basically. So I'm gonna say that we're gonna analyze this when epsilon is less than half, because that's our analysis will need that. Okay. And we can show that the weight update algorithm with epsilon parameters will have the loss of the algorithm to be at most L star plus epsilon t plus something like log n. And moreover, if there is no gain, like the loss is always non-negative, then we get something stronger. Like instead of t here, we get L star. We replace L star by t. We replace t by L star. And note that L star is always at most epsilon t. So this is like a bit stronger. But the takeaway is what? The takeaway is that just from here, it means that the weight update algorithm has no regret, because just by setting epsilon to be like to balance these two terms, basically, if you set epsilon to be like root of log n over t, then you get that like setting epsilon to be root log n over t, then this is what? This is just L star plus basically 2 root t log n. Okay. So it means what? It means that the regret is just which is the difference between our loss and the best expert loss is at most root t log n. So this thing over t is basically less than is like little of t. Okay. So we this guy have no regret, and the second bound here is just a bit stronger because L star is less than t. It's at most t. So that is like when there is no gain, there is only loss, then the total loss doesn't even depends on time. It just depends on like the loss of the best expert. Okay. So this is what we're gonna prove. Good. So this is like really simple algorithm, but like you see soon that like it's really strong, and we're gonna use this like next time and next week. Yeah. Okay. So let's see the proof. Okay. The proof is to like look at the total weight at round t, okay, as a potential function. Like I use capital W to be this one, like the sum of all the weights of all experts. Okay. And the plan that we're gonna do is this. We're gonna say that the total weight after t days, like at day t plus 1, like so basically after all the days, the total weight is gonna be like upper bound by like exponential of minus epsilon a, LA. It means what? It means like if LA is big, if LA is like big, like much bigger than 0, then it means that the total weight must be small. If we make a lot of loss, then the total weight must be small. And the second step that we're going to show is that is something like this. It means that if the total weight here is small, if this guy is small, it's tiny, then it means that Li must be big. Right? If this is small, Li must be big. And it means what? When you combine them together, it means that if our total loss is big, then the total loss of every expert I must be big too. So when you combine these two things, you basically get like just combine the two inequality, which is you get this part, and you get that like our loss is basically as big as like as good as the loss of every expert.
What does the like less than with a tilde mean?
I just mean it informally right now. Yeah, basically like this is just this is less at most this with some small term. Yeah. But this is just to explain the plan of the proof. The actual plan is this. It's just a bit more of the sum term. Like the total weight is going to be basically bounded by exponential of minus f, like exponential of minus epsilon times log, like times loss of the algorithm, but plus ln n here. Yeah. Maybe I write times n. It's the same thing. Yeah. And the lower bound is that like the total weight here, which is going to be at least the weight of one expert I at the end of the day. The expert I is going to be at least, the weight of expert I is going to be at least this. We're going to prove this, which is basically like, think of this as the main term. This is like an error term because epsilon square is like much smaller than epsilon. This is the main term. And once we have these two, then we can combine the two bounds and we would be done. Because, yeah, you can just combine the two bounds, get this and this. just concatenate the bounds. And then take the log and multiply by multiply by 1 over epsilon, then we get this one and this one. And then I rearrange, I get this. And we would be done. So what remains is just to prove upper and lower bound. Okay. So there's gonna be a lot of calculation, but let's do it on the board maybe, just so that it's slower. Okay. Okay. Do you prefer I do it on the board or on the screen? Doesn't
Screen.
on the screen. Yeah. Then let's do it on the screen. Okay. Okay. So let's prove this part first. Okay. Okay. So let's upper bound this one, right? The total weight. Yeah. This is just gonna be the sum of the weight. Actually, I'm gonna do this. Let's say that this is the weight of the t plus 1, like for any t. Yeah. We just write it like this. And then this is just gonna be, I want to write down the weight in terms of day t. But this is just gonna be what? The weight of day t plus 1 is just this one. Right? That's how we define the weight. And basically my goal is to relate W, T, like I just gonna write this. Okay. Good. This is just scaling. And now, so now we have that what is this? This is just gonna be I and like multiply this thing to this and to this and then sum over all I, we basically get this thing 1 minus epsilon pt lt. Make sense? It's just inner product.
So what is the notation?
Oh, this notation is inner product. Right. So, I mean, like, how do I get 1? This is because, like, just this term, like from this term is like a sum of all pi. This is just 1. And then I mean multiply this to this. It's like just like I get epsilon and sum of this guy. Make sense? Okay. this is just our loss on day t, our expected loss on day t. This is our expected loss on day t. Okay. So this is what we get so far. The expected loss on day t. Okay. And so it means what? It means that the weight of at the end, right, is just gonna be the weight at the beginning, at day 1, and product of this guy over all day t from 1 up to t. And how do I simplify this? Like, how should, like, when you have 1 minus something, how should we simplify this? Yeah.
Like the e to the power thing.
Yeah, e to the power of that thing. Yeah. It's so you have that 1 minus x is at most e to the x. Okay, so I just write this is at most and what's the weight of day 1? Of what's the total weight of day 1? N. Yeah, everyone has weight 1. This is n, and this is then like e to the basically sum of day t, and this is LAT, everything times epsilon. So this is just n times, yeah, e to the minus epsilon LA. This is what we want exactly, I think. Yeah. Okay. So that's one part. Like we are done with the upper bound. And next what we want is that we want to show that for all I, we have this thing. Okay. So let's do it. We want to show that Wi at time t, like at the end, it's going to be at least x minus and minus. Is it plus or minus here? Maybe it's plus, it's minus. Okay. Okay. So let's try to reason about this. Okay. Like just try to write down again the weight of expert I. This is just the weight of expert I at day t. Okay. Is just gonna be the weight of expert I at day t plus 1 is just equal to this one. The loss so we can then write the weight at the end is then just the weight at the beginning at day 1 times the product like before. Okay. Sorry. Summing over all t, right? T from 1 to t. Okay. What is this? The weight at the beginning is 1, just 1.
Sorry.
Yeah. In the beginning, this is just 1. So we just need to analyze this. What should we do with this? Basically, it's basically like before. This is what you should keep in mind. But when you write down the upper bound, this is always true. Okay, but it's not like quite true in the lower bound. Like we need to like take care of some error term. Okay, so but you actually have this like actually let me write this. You have this thing as well for when x is like not too big, when x is like maybe less than 0.5. Okay. But yeah, like but the point is like this is tiny when x is tiny. So yeah, but you need to be careful. You need to put this one just because to make the math like formal. Okay. So let's apply this inequality. So this is just maybe I do it more slowly. This is then still a product t, but now e to the minus epsilon of L1 Li and also yeah, maybe I write down epsilon Li and epsilon Li t square. And then we can just put the product on the exponent, which is just a sum. Okay. So what's this term? It's just this term, right? This is e to the like minus epsilon Li. This is just the loss of x plus I over days. And then minus epsilon square sum t this thing square. So we don't have a good way to bound the square, but you know that it's between 1 and minus 1. So let's say that this is at most 1. This thing square is at most 1. Summing over t days, so this is just t. So this is at most, sorry, this is at least minus epsilon t, because Lit square is like at most 1. Yeah, that's it. Yeah.
So one thing I'm confused is like then can we like say that instead of multiply by 1 minus something, we just multiply by exp something logarithm?
Multiply by what again?
Like multiply by xp. So that's originally the
XP.
we multiply 1 minus epsilon Li logarithm. Now can we just do exp here?
Oh yeah, we can. Yeah. So you ask like good. So Ben, your question is that what if in the algorithm here, instead of multiply by 1 minus this thing, what if we just given our insight that this is just basically this thing? What if we just multiply by exp minus this thing? It's gonna work. because it's basically the same. Also, like when you write down the analysis, there's gonna be like some tiny bit of careful, like different kind of carefulness that you need to take care of still. Yeah. When you write this thing down, there's a name for this. It's called hedge algorithm, like hedge, like a hedge fund. It's the name in machine learning. Yeah. But it's basically the same algorithm. Yeah. Nothing different. Okay. So I hope we are good. Like, so this analysis, you see that it's not too hard, but it's a bit of algebraic proof, not too insightful. At least, I don't know, a bit of algebraic manipulation. But the point really is that this is the point. The point is that we want to say that if our loss is big, then the total weight must be small. And if the total weight is small, then the total loss of any expert is big. And just combine them. Okay. I am thinking if I'm gonna teach you how to derive, like what there's a different analysis that is more intuitive, but it needs more background on analysis. Like you need to know gradient and Hessian. But maybe I don't do that. Yeah, but I might put it online just if anyone is interested, can look it up. But this is like the proof that usually appears in other courses, but there is a more intuitive proof, but you need a bit more background. Okay, so you have this, you combine them, you're done. Okay. By the way, like when the loss is between 0 and 1, you can get a stronger bound, or when you try to get a lower bound, like just be more careful. Use some algebraic trick, and you're gonna get like that. This is L1, Li instead of T, and just by getting this improved lower bound, when you combine the two inequalities, you're gonna get this one at the end. So replace T by Li. So that's a bit better, right? Because like this is like you are as good as expert I with a multiplicative factor of 1 plus epsilon, not just like an additive epsilon T. Anyway, this is just some details in the proof. Just want to mention that you can just rewrite everything in terms of gain instead of loss. Sometimes it's just easier to think about when you think of gain instead of loss. That is, okay, like just say that on each day the adversary review the gain vector GT, right? And then the gain is just the total, like this one, which is just the negative of the loss. And just rewrite everything in terms of gain. So now you just replace the update of the weight by the update of the weight like this. Okay. And you can see that like once you replace everything by gain, then you just get basically the same thing, except that you revert the negative, like the sign on each negative become positive and so on. Yeah. So you get the same kind of bound here. That is, the gain of the algorithm is as good as the gain of the best expert up to some small factor here. So nothing interesting here, but like it might be more intuitive to think about in the future. Okay. Let me discuss the history a bit, right? Yeah. Multiplicative weight update is actually a special case of something called follow the regularized leader. So you have seen the follow the leader algorithm. That is just to follow the best expert. That is bad. But what we are doing here is actually like, as you see, it's like softer version of follow the leader. And there is like a formal term for this. It's called regularized leader. So you try to like kind of still follow the leader, but not too strongly. Like give yourself some chance to follow someone else too. Okay. And actually gradient descent also follow like it's captured by this algorithm, this framework too. Like this framework is something that capture both multiplicative weight update and gradient descent. You might have learned gradient descent somewhere else, I'm not sure, but it's really good algorithm too. Yeah. And the area of this is called online learning. Not in the sense of doing it on Zoom or something like that, but like you try to, like learn which expert is good in the online fashion. Yeah. Yeah.
Wait, you said it generalizes gradient descent, but isn't gradient descent deterministic? So would it be like it generalizes stochastic gradient descent, where it's like it actually has some elements of randomness?
So gradient descent is deterministic. You can think of multiplicative weight update as the deterministic algorithm too, but it's deterministic in the sense that it chooses the distribution deterministically. Yeah. So like gradient descent also like choose a combination of direction deterministically. It doesn't just go on one coordinate. Yeah. So they are both deterministic in this sense. And if you think of coordinate gradient descent, then like it chooses each coordinate according to this distribution. That it's anyway. Yeah. Let's not go there. If you want to learn more about online learning, go to this lecture note by Luca Trevisan. I put a link there. He's super amazing researcher. Regret like sadly he just passed away like a year or two ago. Yeah, he's super nice person. I love the time with him. Okay, but this algorithm weight update here is actually discovered independently many times. It has been discovered by John Watt in the von Neumann in the context of game theory first, and then used in machine learning, and then again later discovered for a LP solver and flow algorithm that we will see how to use it for. And then people realize that okay, they are all the same. Yeah. And yeah, so philosophy sometimes asks is math invented or discovered? So some algorithm clearly is discovered. Some algorithm clearly is invented. It's quite artificial. You just try to solve something. But this one is really, I think it's really out there. It's the one that is discovered. It's there before. It's even there in literally in the sense that people study biology and discover that how genes try to evolve itself in evolution, it follows this algorithm. So if you want to look at, you can go to this link. I put it there. It's quite interesting. So next 3 classes, we're gonna maybe 2 or 3. We will see the power of this algorithm. Yeah. Okay. So see you next time.